Okay, let's get started with Lab 9 for AGEC 305. This is our Friday meeting for week 12. It's also going to be our last sort of serious look at the value chain in agriculture. We might come back to this just a little bit in one more lecture, but this really closes out the topic of substitution possibilities and sort of the farm resources to uh, moving from so here in our picture, from farm resources to food output. um, so let's look at what we have here. So the key piece as we move up through here between farm resources and to farm outputs, and then further processing to something that's going to be food that's bought at retail. um, the cost of production of the food good and the farm good, right? So how are the costs split up between these two branches? This is what we call a tree structure of the ag value chain. So, sort of level one, level one, level two. I'm counting from the top. So the cost structure between these two things, and then how easy is it to switch them out, to substitute them, and still make the same farm good. And then the same thing here. What's the cost structure between the farm good and other inputs that get used in food, and how easy is it to switch between them and still produce the same output? So that's our story, a big story that you could think about is, well, this is something that nobody makes, right? Land is just there, and farm producers are the primary users of land in terms of turning it into sort of a valuable, using land to make farm goods, or to make a valuable product, right? The demand comes from for ag land, comes from farm production, and then so that means that there's price impacts between land and farm production. And then if it's the case, right, that food uses farm goods, the production of food uses farm goods, and there's a price relationship there, then that price relationship carries all the way down. So that when we see food demand changes, we should be able to track them all the way to land. Now that's not going to be a task of ours in this class, but you could see why both levels of the tree work together, and we're going to look at them independently. So let's look back at Lab 8. We were focused on the sort of part down here in the blue box, and here we focused on the substitution between land and other inputs and what that meant for prices. And we saw that if the substitution is low, if we restrict the substitution, then shocks or demand, as demand for the farm product goes up, the land price pressure goes up by a lot. And that's, that gives us an idea of just how strong that relationship is. And it also means that a lot of the pricing value, right, if you're a farm producer and you're renting land, a lot of the benefits of demand shocks could be passed on to your landlords, right? So a lot of the wealth accumulation in agriculture, the sort of long-run income gains, may sit in owning the land, right? Because it is the most scarce sort of factor in all this. Okay, so that's sort of question one that exists in this value chain, and it's an important one. We made some special assumptions that land was perfectly inelastic and non-land. So this was fixed quantity, this was fixed price. Non-land is perfectly elastic. So you can get all of the chemicals for production, or fertilizer, which is mostly organic, chemical, a chemical process as well, machinery, fuel, that you can drive up the ag demand for those inputs, but ag is such a small part of the total demand that you're probably not going to change the price much. So we fixed that price, we fixed this quantity, and we got to see a real focus on substitution and just how much pressure goes on the land rent when you can't increase output using yield increasing substitutions. If we switch over to the top level, we have this different question. So if the question there was about how much sort of the demand for agriculture gets tied up in land rents, well, here, how does the demand for food compare to, that drives up prices for food? How does that relate to prices received by farms? And so if we look at this, let's just talk about our top level here. This is sort of food processing. We're not really saying it's the retail food dollar, but that's sort of the notion here. So it's something ready to eat, ready to sell for its end use, and just as a generic name, food processing is as good a name as any. Obviously, there's all kinds of things. There's a steak at a really good restaurant. There's a hamburger at McDonald's. There's ground beef at the grocery, and so there's all kinds of things that go here. But as a simplified case, let's think about what we have. So we have this food processing, and then we have the farm level good, whether it's a side of beef or a fed animal that needs to be fed farther, however you want to think about what the farm level good is, and then it gets combined with other inputs. Okay, so typically here we're talking about grain, right, that's hauled and delivered to an elevator where it'll be purchased and milled or whatever sort of the next level of processing is. And typically we're talking about live animals off a farm. In most cases we would talk about animal ready to be fed to its kill weight when we think about this. So the exact sort of definition that we use right here will give us an idea about how much substitution is possible, because the more levels in reality that exist between farm product and sort of the processed food output, the more levels that exist, the more substitution possibilities exist, the more chances there are to bring in another input that makes up for some of the cost in the final retail dollar. Okay, well, there are two markets here too. So remember last week we talked about there's a market for the output, and then there's a market for each input. So there's 3 total markets, and we can last week we made assumptions that the supply was fixed for one side and the price was fixed for the other, so we didn't really need to think about the supply side. But this time we are going to think about it. So we're going to build up a supply elasticity or supply equation for farm production, a supply equation for these other inputs. Let's think about the elasticities for other food inputs. Again, those are going to be labor, refrigeration, energy, other things that you think about, and corn, right? Animal feeds, all kinds of things. And not just those feeds, but the way you can mix those feeds and make adjustments, and the types of ration that you can put together for animal feeding. So there's all kinds of stuff that goes over here, and here we're just talking about whatever the closest relative of off-farm, of farm gate product to the final product. The supply elasticity for farm output, well, we've already had once a restrictive assumption on land and said it's very inelastic, or perfectly inelastic last week. So if it is very inelastic, that's going to translate to the farm product, right? So the substitution here would determine the supply elasticity. So let's just make it small. So let's say that we know that this side is going to have a relatively large supply elasticity and relatively small here. And then the final part is, can we substitute, and why do we care? And that's sort of where does the pricing, where does the price analysis part come in? And it turns out we do care, right? Because if we have one side that has a small supply elasticity, another one with a large, If we're able to substitute, then we are able to make better use of these other inputs in the final processed product, and we are not so beholden to the pricing relationship that exists between the food in its final form and the farm level product. Okay, let's think about the ag value chain here. When demand is shocked, so more output is required at this level, we know that increases the food price, right? So we get our law of demand. This goes up, so as the quantity goes up, so does the price. And then we want to know how much price pressure moves down this leg of the value chain tree to increase the farm production price, right? So how much of that demand shock ends up here, just with, like when we did last week, the more substitution that exists here means there's less pressure on the prices at the farm level. And if it's very low substitution, then that pressure is passed equally to both sides, because you need to increase the demand for both inputs to make up for that. And so that gives us a chance to this is something I did in class on Wednesday, just kind of in passing, but I wanted to preview this to think about the theory of these input markets and the price changes. So let's think about this is a market curve, right? So supply, demand, quantity on the horizontal axis, price on the vertical axis for our ag input. Okay, so this is the farm level product, but it's an input in the food market. Okay, so when we make the final good food, ag or farm product is the input. So we're talking about this market right here. This is the only one we're going to think about. So we're going to think about shifts to that. Okay, so you get this demand curve that comes from the food processing requirements, right? So it's a derived demand curve. It comes from whatever the technology is to make food. The supply curve is built from farm production, so it has a supply elasticity based on how easy it is or how price responsive farmers are. Let's start with our shock. Our shock is to the final good, food, and when we shift the demand for food, we shift its derived demand, right? This point labeled 1, we shift the derived demand for the ag input. Okay, I want to keep calling it the ag input here because it's the input, the agriculture side input to food. Okay, so the food demand shock causes them to require more of the ag input for production. We get an initial effect here. That shift has this price effect. Okay, so the shift in the demand curve forces quantity and price to go up at the same time. That's what we call a positive demand shift. And so these derived demand curves work the same as any demand curve we've looked at. But there's a second effect here. Okay, so if you look at the demand equation, sort of a simplified form of it, this is written in percentage change terms. This X is the change in demand, the percentage change in demand for the input. Quantity, the Q, is the percentage change in the demand for the output. And so this is the food variable. That's our shock in this model. This is the ag input that's used to make food, and that's an endogenous variable. And so the sort of basic assumption, or the first round assumption, is you shock food, that pulls up this value, right? So imagine this term here goes away, the sigma p minus r. Shock this up, you need more of this input. Okay, so the Q at the end of this percentage change equation is this shift right here. Then the second part of it comes from market clearing. So that shift corresponds to moving up this supply curve, this price increase marked by 2. Okay, so we get that shift as it's mentioned here. So that shift or that impact in the ag product market follows that shift of the demand curve so that you get this price increase. But now let's go back to our equation. We get this price increase, and so I'm sorry, that should be an R. we're talking about the input market here, so that's really the R, the rent, or the rate of pay for the ag input, because it corresponds to this lowercase variable. So when the price increases for the ag input, this R is the price of the ag input, right? So this piece right here is the thing that's going up. So whatever the substitution elasticity is, multiplied by this negative R term, right? So sigma times negative R means that you're going to tend to get this first shift that comes from the variable Q, and then the second part is going to be to back down. So whatever the full shift was just from the Q part, you're going to back down because the price in the ag market, the price on this axis that would be better represented by an R, is going to reduce. It's going to cause a reduction in demand. Okay, you're going to get a second shift. So let's follow this through. So again, my apologies. This is the price for agriculture, and it's really should correspond with a capital R to match this lowercase r. So as the ag price goes up, sigma tells us how much. Okay, if the shock from Q says shift it this much, and then when the price starts to go up, the substitution elasticity tells us how far do you want to back down. Okay, if it's large, you're going to back down a lot. If it's really large, you may actually reduce demand here. Okay, so that's the question we're after. And so let's add the third point. So the initial shock, the Q part of the shock is shift this demand curve out to here. The reaction in part 2 is the price goes up, and then as that price goes up, you get this new reaction, which is marked as 3, which is you start pulling the demand curve back down. Right? This all happens simultaneously in the equations, but we can separate these out as to the expansion part and the substitution part. So if we're able to substitute using sigma, right, the substitution between ag and non-ag inputs, then it must be the case that the final effect is to get this initial shift up, but it backs its way back down as that price gets pulled up into. Okay, so that reaction. And so this is the substitution effect. So the first part is the expansion effect. The second part here is the substitution effect, meaning that we are sort of eroding, whatever this shock was, part of it's going to go away if we're able to substitute for the ag input. Okay, so let's keep going. So the final outcome is a smaller net shift. So we are going to get the price, as the demand curve shifts back to the dotted sort of blue line in the middle, then that full increase of the price doesn't happen, and it starts rebalancing itself. Right? It's sort of like keep drawing new demand shifts that are just a little bit under here. Recheck the price and see if you want to still substitute some more. Okay, and so we said it's going to end up all the way at 3, which means that our final price effect in the ag market is going to be 4. So, or the net effect will be to the dashed line. Okay. And so what's the substitution's role? Well, that's the role of the price relationship. So you end up with the final market is going to have some demand shift, and it's going to be give you some change in the final product price. The substitution role is to change us from not having to feel the full effect of 2, the price increase of 2, but instead getting the price increase of 2 and then take away the price decrease that comes in 4, so that you end up with this smaller price change as measured on this axis. The role of sigma is to tell us how far this shift can go. Okay, so if the full sort of expansion shift is 1, then this substitution shift is 3 is completely dependent on how big that substitution elasticity is. That's why we care about measuring the substitutability between these things. Okay, let's look at our Lab 9 model, and I'll pull up the spreadsheet that you are given here in a second. So there's going to be a little bit of a change. Instead of just having these three parameters for the ag cost share, the non-ag cost share, and sigma, you also have a handout that you can read to get the changes to the names. But this is basically the same spreadsheet we had last week. Except for we are now going to have a supply elasticity for agriculture and a supply elasticity for non-agriculture, and that's going to change equation 4, where the supply elasticity will now show up, and equation 5 here, where the supply elasticity for non-ag shows up. I give you a base assumption in the spreadsheet. It looks like this. So the ag cost share is 0.25, the non-ag cost share is 0.75. This is just the starting value, so we're going to actually change these assumptions. Substitution elasticity is 0. The supply elasticity is very small for the ag product. For the non-ag product, it's quite large. Okay, so that gives us a starting point. And look, it gives us the same result we had last week, more or less. So the ratio of the output price to the input price is exactly the cost share when there's no substitution, and these elasticities are small and large. Okay, so it goes to this inelastic goods cost share. Okay, so for our actual experiments, we're going to set them up to look like this. So the supply elasticities, I think 0.5 and 25. We're going to do two different sets of cost shares, one where it's 0.3. If you remember in the slides I've been talking about, that kind of corresponds to fruit and vegetables, having a cost share of the ag product that's about 30%. And then for meat, it was closer to something like 60%. And so that would be our two changes. And then what we're going to do is sort of play out our theory steps. Okay, so I've switched over to my spreadsheet, and this is the spreadsheet I'll give you. So it'll have last week's model in it, as well as the tab for food model. And here are the starting values that are going to be there when you open it. Sorry. And yeah, so let's reiterate. So we get this cost share, the price ratio, or this is the ratio of the percentage changes in the price, PF, to the output price for food to the ag input price is 0.25, and that's the same as the ag cost share because we have no substitution and a 0 supply elasticity against a very large supply elasticity. Okay, but that's not the interesting sort of way to look at this farm to retail problem. So let's think about some realistic assumptions. So I think on the last slide there, we talk about some assumptions that will work for us. So let's reset this to those. So I'm going to start with 0.3, and that converts the non-ag cost share to 0.7. And then for the supply elasticity for ag, I say let's make it inelastic, so it's small. We'll put 0.5. And then for the supply elasticity for non-ag, we're going to make it large, but not quite as large as we have been, 25. Okay, so that gives us a full set of results here. And so the first thing I want to do is think back to our slideshow. Bring that back up. Right here. So part 1, part 2, part 3, and part 4. Okay? And so if you think about what we're doing in this spreadsheet model, we can measure part 1 and 2 right? The full shift of the demand curve and the full price increase by not allowing any substitution. So if 3 and then 4 are allowed, or are a measure of this reverse shift to the derived demand curve is a measure of how much substitution is there, then we can turn that off by setting the substitution level to 0. And so that's what I want to do in this. So what I want to do is look at the change in the demand for the ag input here and the price of the ag input here. Okay, and so those values are 1 and then X demand A. Actually, that's the one that's 1 and this one's 2. And so this is just the expansion part. Okay, and so now we had the sigma or the substitution elasticity turned off, and let's set it to some other value. And so what's a good substitution elasticity that's low? I don't know, I'm just going to pick 0.5 and go with it and ignore this stuff over here changing. That'll be for one of your, we'll talk about that in a second. And so we turn the substitution back on, and now we get the full effect. Okay, so we get the expansion part happens and the substitution happens together. And so when we get the full 1, 2, 3, 4 effect, the demand now is 0.6, right? It goes up by 0.6 and the price goes up by 1.2. Now if we want to pick out what's the substitution component, then all we have to do is subtract the full amount is equal to this. So the substitution component must be the part that reversed, so 1 and 2. Okay, so it's going to be the full effect minus the expansion only effect. Okay, and so if you want to think about it in terms of the graph, this is 1 and 2. This is 3 and 4. And this is 1 to 4. So this is everything. So this is kind of this backwards analysis where we look at, first of all, what happens if there's no substitution? Bring back the substitution and we get the full effect, and then to do the analysis to see what contribution substitution had, you need to compare these two numbers, and in fact we can pull those out and say, well, of the final price effect, it's the substitution reduced this by negative 0.8, or you can think about that as 40%. Is that right? Yeah, 40% of these effects are reversed due to substitution. Okay, and that's with a fairly low substitution elasticity. You can reverse those more and more, and that's where we'll go next. And so the only thing I'll ask you to do, so in the quiz, you're going to be changing this ag cost share to 0.6, so it's something more like so if we're saying that 0.3 is sort of the vegetable case and 0.6 is sort of the meat case, then in your quiz I'm going to ask you to do these calculations, the exact same ones I did here. First, set the substitution elasticity to 0, then change it to 0.5. So you collect the numbers here and then collect them here, and then do this subtraction, and you'll get how much of the effect of this solution is brought on by the substitution effect, okay, using a 0.5 substitution elasticity. And is it different when it's 0.6 or not? So that'll be the first two things on your quiz to do to replicate these steps. Okay, and then the second part that I want to look at is built for you right here, and this is what we call a data table. And so what we have going on here is this is the price, the food to retail price ratio, or sorry, the retail to farm price ratio. And so this cell right here is tied to the retail to farm price ratio that's written right here. Now this is in percentage change terms. So what it's showing us is how much is the final good, the retail price increase compared to the farm price increase for all of these experiments. And so what we have on this column, let me drop that out of our way here. So what we have on this column are values for sigma. And then for each of these columns we have sort of scenario 1 and scenario 2. Scenario 1 is a cost share that is 0.3. It's tied to this cell, and it's basically the case for vegetables, where it's about 30% of the retail dollar is the farm product cost, the farm vegetable cost. Here, meat is a higher cost share. It's 60%, and that's saying that 60% of the retail cost of meat is tied up on the farm, right? It goes back to the farm as cost. And so the two things, so the two different scenarios are in each column, and what we've got are a bunch of substitution elasticities from very small to very large here. And so the thing I want you to make note of in this graph is just how much how these two things differ. So you see when it's a higher cost share, you follow this curve, but as the substitution elasticities get large, right, the substitution elasticity down here, as it gets larger and larger, everything is going to 1. So they start at very different points and they follow different paths for lots of the substitution possibilities based off of their different sort of cost structure. But at some point, if it becomes very, very substitutable, then the price of impacts go away. And so what are reasonable values? I don't even know, but we could reset this to look at those. But we want to see, first of all, how the math plays out. And then the second thing we want to do is say, what if the supply elasticities for agriculture aren't the same for vegetables and meat? Or what if 0.5 is a bad assumption? So we can start making some changes here to see how the graph adjusts. So changing it from 0.5 to 1 doesn't change much, but to 2, you can see the shifts that are going on. And now let's try something that's really big just to see the graph change. Whoa, too big. And so as you keep adjusting this, you'll see that they keep squeezing together, so the changes have less and less effect. Okay, so as the supply as the supply elasticity for agriculture grows towards the supply elasticity for non-agriculture, we squeeze these together and the substitution effect matters very little, as does the cost share effect. Let's set this back to where it was and now increase the supply elasticity for non-agriculture. And you see that the difference in the ag side, as the supply elasticity for non-agriculture gets large, the cost differences on the ag right here, the vegetable being 30% of the cost, 60% of the cost for meat, matters more and more for a farther distance, right? Even at big substitutions, you still get this gap. And so let's change it to something like really large. And you see that you end up with, if it is the case, right, that the inputs, the labor that that food processing uses, and the servers has a very high supply elasticity, very large, that that you can keep hiring people at roughly the same price without driving up the labor market price, then the key factor becomes what is the cost share and how substitutable is it. Okay, so now we can try this and see if our effects show up, and see you can see that it's being driven by that cost share. So I'll give you some you'll have some quiz questions that you have to pull out of these graphs, but there'll be things that you can pull out of these tables. So this graph is just plotting this column of points on the blue line, this column of points on the orange line. Okay, but what we really want to focus on is this added sort of dimension that we put in, that we now have supply elasticities for the two inputs. Okay, and just keep in mind, we're doing the same shock to all of these. Every time, everything here is being driven by a 1% increase in demand for food. I guess the final thing that we should make sure that we understand is this is the retail to food, the retail food to farm good price ratio. This is how we're measuring it in percentage change terms. And so let's set this to very low, and you get 0.314. Increase it to the value we just had, you get 0.3275. Change it again to 1. You now have 0.304. And that's what's being calculated right here, right? These are increasing values of substitution elasticity. This is the food to farm price ratio. And so what we really want to point out, what I'm trying to point out with these numbers right here and with these graphs is, as substitution goes up, as substitution goes up, the food price increases faster than the farm price. And so one of the things that we've learned about food production technology is that if it's possible to substitute for the ag good, and you make value added, you make meals away from home, you make ready to eat microwavables, you make cereal that's packaged with air in it and a toy or whatever. As you make things that substitute for in the cost of the product at retail for the food good, as you're able to do that, then we are going to see food prices move differently or faster than the farm price. And that's what this is showing. As the substitution for whatever food good you're talking about and whatever the initial cost share, as the substitution goes up, if you move down through these points, that are being plotted here, then all of these numbers that are increasing going down this column say that this value, the fact that the food price rises faster than the farm price, as substitution goes up, the food price will be allowed to rise faster than the farm price. And that's because you can draw in more inputs and because the elasticity of supply is small relative to the non-ag inputs. And that's really the story that we want to tell in farm to retail. Okay, and that means that before we say anything, and this is really the story of agriculture and agribusiness and value chain, before we start saying anything about how much competition and whether anything is fair to agriculture in the food production business and in the retail side, we have to first understand what the substitution relationships are, because those are what control the price effects, whether we're talking about it in ratio form, the food to farm ratio as it's measured here, or whether we're talking about it down here where we broke it out in terms of an experiment where we said, first let's get the full expansion effect, the demand effect for food. Now let's do the full solution when we allow substitution, and let's see how much of the fact that the farm price isn't going up the full amount is due to the fact that you can substitute other inputs for it. Okay, I think that should be good for our lab video, our lab walkthrough. Let me just pull back the slides to see what is at the end of those. Yeah, and this is just the playing out that theory scenario that I do in the spreadsheet for you. Set these values, do the 0.3 case, the vegetable case right here. Set the substitution elasticity to 0, you get the pure expansion effect. Demand goes up by 1, price goes up by 2. Set the substitution elasticity to 0.5, and you're getting the final effect, 0.6 versus 1.2, and then compare 3 versus 1, and you get the part of it that's contributed by the substitution. So negative 0.4 to the demand, negative 0.8 to the price. And that's what you're asked to do only for the case when it's 0.6 in your quiz. Okay, so that'll close it out, and I'm going to shut this down and start working on your quiz.